welcome to lecture number 58. Here another interesting theorem is there, which is not really solving a network theorems, but it is called popularly known as maximum power transfer theorem. It says that in a network between any two terminals, what impedance should I connect, so that power consumed in that impedance or called load impedance will be maximum, power delivered to the impedance is maximum. To begin with, let us tell you that you have a network here, linear network. Suppose resistive network, we will see also for the AC circuit how it looks like. You pick up any 2 points. Then here I am going to connect the load impedances. I want to know what should be this load impedance ZL, or if it is resistive network, it is some RL I will connect. What value of RL will give me maximum power? To do this, behind A and B, this whole network can be changed to some R Thevenins and E Thevenins, B Thevenins, is not? Then these 2 points A and B, and then the load resistance here. So, the problem can be simplified in this fashion. Therefore, to find out first the maximum power transfer theorem with DC circuit. So, in DC circuit, it will be like this, that you have I will consider a battery having a voltage E, open circuit EMF, these are the 2 terminals of the battery, and here is your RL. This I will go very quickly and without not much maths. So, and this RL I am going to vary. As you can see, if RL is equal to 0, output power will be 0, because there will be current, but RL is 0. Similarly, if RL is very high, are you getting? Suppose I am plotting here power versus RL in this network. So, for any finite value of RL, the value of the current will be E by RS plus RL. This will be the current, and power in RL, this P is equal to I square, that is E square by RS plus RL whole squared into RL. What I am telling, if RL is 0, then power is 0. If RL is very large, infinitely large, it is RL by another, this is RL square. So, then also power will be 0, and it is a smooth curve as a function of RL. Therefore, I must expect, so power was 0 here, at RL infinity also it was 0, but for finite values of RL it gives you a positive number. Therefore, this power must have gone up, reached some maximum value, and once again has started coming down. That must be happening. I want to find out what is this value of RL, so that you get maximum power, P max. The answer to this question is very simple, that P is equal to E square. E, mind you, E is constant, RS is constant, you are valuing RL only. So, E square into RL divided by RS plus RL whole square is the expression of the power. Now, therefore, it looks like you differentiate this dP dRL, equate it to 0, you will get the values of RL. But only thing is it can be, that calculation can be simplified if you just do like this, this you break up R L square plus 2 R S into R L, and there was an R L here, and this R L you bring out below this one. So, it will be R S square by R L plus R L square by, I am dividing both numerator and denominator by R L, and then plus 2 R S. So, power will be maximum if the denominator is minimum. Therefore, I will, instead of trying to differentiate this whole thing, which will also yield same results, but there the thing is R L is present in the numerator, denominator. So, that computation becomes a little not tedious, but compared to that this is much simpler. Why? Because it is there. So, I conclude. So, P will be maximum if this factor R S square by R L plus R L plus 2 R S is minimum. That means d R L, I will set it to there, equal to 0, and if you do it, it will be minus R S square by R L square. With respect to R L, I am differentiating, this will be plus 1 and this will be 0, that is equal to 0. This will be the thing, because R S is constant. I will not going to change R S, source resistance and EMF, same battery. So, from this I conclude that R L square is equal to R S square, or R L is equal to R S, knowing fully well that this R L will be a positive number. So, this will guarantee the minimum numerator, denominator means maximum power, and one can calculate the second derivative and verify that really it is minimum or not. I am not going into that. Therefore, we conclude that if you vary R L, so maximum power will be delivered for a battery. The conclusion is this is the source, E, here I am connecting R L which is varying, and what I got is this one. This is R S, and if you connect a resistance here whose value is R S, if R L equal to R S, then maximum power in R L will take place. Maximum power will be dissipated in R L. And only one additional information I will tell you about this maximum power transfer theorem, that maximum power will be consumed by the load resistance when its value is equal to source resistance, that is in language people say load resistance should be equal to the source resistance in case of DC circuit for maximum power to occur in R L. Okay, that is fine. Now, but you know the impedance of the load is not in our hand, it depends upon the application. Our application requires some voltage to be applied across it. R L is really not in our hand, but it is worth noting that what is the efficiency under maximum power condition, under maximum power condition. What do I mean by efficiency? Efficiency, you know, is the output power, that is in RL, power in RL divided by power delivered by the total power delivered by the battery. By the source. Is not total power delivered by the source. Now, what is power in RL? Under maximum power condition, it is I square into RS. This is the power delivered in RL, because RL equal to RS then. So, I square into RS is the power delivered by the source. What is the input power? Two ways you can calculate. It will be the output power, that is I square into RS plus plus another I square into RS, which will be lost inside the resistance. So, that mind you, this RS I have got RL equal to RS. This RS I have put RL equal to RS, is not output power, power in RL when RL equal to RS, that is what I am meaning. So, I square RS and input power is this output power plus the power loss in this resistance, that is the total power delivered by the source, and this will become equal to half or 50% in percentage. Therefore, maximum power condition, if you put RL equal to source resistance, okay, maximum power will be delivered, but efficiency of this overall system will be only 50%, not a very good situation. So, the point is, this curve if you plot here some P max, here if you put RL and here you put power in RL, then I am telling at RL equal to RS, this P max occurs. This is the P max. It is it may be some people may be interested after knowing this, okay, maximum power will be delivered, then I will always try to maintain RL equal to RS. But you really cannot do it, because load impedance is not to be decided by input power condition. Even if somebody insists that no, always connect impedance, load impedance to be equal to source resistance, okay, you will get maximum power delivered to the load, but the point is efficiency of the system will become too poor. So, this is not a very good proposition. However, in case of low level of power in electronic circuits, say amplifier circuit, etc., where power itself is low, efficiency does not matter too much, there people will always see for impedance matching, so that maximum power is delivered, is not in your sound system. Okay. Output impedance of the load speaker should be same as the input impedance. So, that maximum power loudness is important there. Sacrifice efficiency at that low level, how does it matter? Anyway, this is how this is the maximum power transfer theorem in DC circuit. Now, things will be a bit complicated if it is AC circuit, maximum power. In AC circuit. By AC circuit I mean sinusoidally excited, sinusoidal voltage source excites this circuit, excites this circuit. How the source can be modeled? AC source, it is like this, and the internal impedance of a source or generator will have now a resistance R s as well as a reactance J x s. Got the point? Because all generators are some coils moving in a magnetic field, therefore, that can be modeled as a series impedance of winding resistance as well as reactance, nothing like capacitance R s and minus J x s, not less. So, these are the source terminals A and B, and here is a fixed voltage, RMS value is suppose V, say V angle 0 degree is the voltage applied. AC source, so I will apply phasor, and I am considering the circuit is operating at steady state condition. Okay. Now, here I will connect an impedance ZL, which will have once again two components RL plus JXL. If this XL, if this XL is positive, it is inductive circuit. If the value of the XL is negative, it is capacitive circuit. And I am telling that I will be varying both of them. The question is, what should be ZL, so that real power consumed in ZL is maximum. This is how the problem should be stated. Okay, RL, XL you arbitrarily connect, you vary them. This is the source impedance. This is source impedance, constant. This is the supply voltage, constant. Therefore, what should be this value of RL and XL in terms of say Rx XS, so that power in ZL will be maximum. So, power, expression of power, now for any arbitrary value of RL and XL, power will be maximum when, what is the expression of power? Current square into RL, that is the expression of the power, real power. So, that real power is I square into RL, which happens to be equal to this voltage into current into cos theta of this circuit. We know that, is not. So, power consumed in this load impedance will be, the expression of that will be simply I square into RL, I is the RMS value of the current. Now, what is the RMS value of the current? RMS value of the current will be the supply voltage RMS value divided by the total impedance of this circuit, which happens to be series in nature. So, it will be RS plus RL square plus J YJ XS plus XL square, is not, under root. This is the expression of the current. So, put it here. So, it looks like it will be V square. This is algebraic equation, mind you, voltage by impedance decides the RMS current, we know that. So, this will be then equal to V square into RL divided by RS plus RL squared plus xs plus xl square. And in this expression, you know, what are the things I will be varying? I will be varying RL as well as XL, other things are constant. I want to find out what should be RL and XL. Now, it looks like there are two variables here to decide the power, because I will be going to change both RL and XL. Now, to deal this problem most efficiently, what I will do it, try to understand this step. I will first choose any value of RL, any fixed value, and keep it fixed. For example, RL equal to 2 ohm, and I will try to find out the condition of XL so that power will be maximum there. Got the point? Instead of varying RL and XL simultaneously, now this step is very important. Then you can save lot of time in derivations, differentiating things, just like that. What I will do is this: let RL be fixed at some particular value, any particular value. Say RL equal to 1 ohm, I will not vary RL, XL only I will vary. So, in that case, what I am telling is, that is this problem of getting this value of the load impedance for maximum efficiency, I am doing in two steps. First step, I will fix RL to some any arbitrary value, I will fix it. Then I will say that if that be the case, then power in RL will be P is equal to I square into RL, is not, and RL being now fixed at a particular value, when power will be maximum? When I is maximum. When the RMS value of the current is maximum, then only power in this RL will be maximum, is not. I will vary XL, a particular value, and XL is only varied, XL is only varied. So, under this assumption, I know what will be the power in RL. Power in RL is I square into RL, I square into RL. RL I have made fixed. Who is changing then? I is changing. What for? Because we are varying XL. Which value of XL will give maximum RMS current under this scenario? So, P will be maximum, P now will be maximum if I is maximum and I is this expression where RS RL is fixed. In this case, the same expression is valid now for I. Now, I am telling RS RL I have now fixed, I am not changing RL, XL only I will vary now. Then when I will be maximum, does it require any derivation? I will simply say I is maximum looking at this expression if the value of XL is equal to minus XS. then only it will be maximum, otherwise how? Got the point. But then you will say, look, you have still not completed your solution. You have simply said that if XL value is chosen to be minus XS, then you will get maximum power in RL for a particular value of a RL. Now, to maximize the current, no matter what is the value of RL, XL must be set to minus XS. So, I then conclude that here now I then write that. Now, what we have got? In the circuit, this is your RS JXS, JXS say. These are the two terminals. I have got one thing, maximum power will take place if the load impedance is set to this value for a particular RL. So, for a particular RL, if this is the thing, current will be how much? Current will be this voltage divided by RS plus RL, is not under this scenario. No matter what, suppose you choose RL equal to 5 ohm, I will say maximum power will take place in this RL equal to 5 ohm, provided the load impedance is 5 minus JXS. JXS is fixed. If somebody chooses 8 ohms RL equal to, then also he will say maximum power will take place when XL equal to XS. Of course, the level of these two powers will be different, that is different issue. Therefore, essentially once this is chosen, I will now play with RL, and this circuit this RS, the magnitude of the current, this circuit becomes a unity power factor circuit looking at this. So, this is equivalent to RS and here is RL, is not what else. This is equivalent to this, and this case I already know when the maximum power will take place, when RL equal to RS, is not. The moment the reactance value of the load impedance is fixed, it has to be minus JXS, then only current can be maximized, RMS value of the current. Therefore, I will say now with this choice of XL choice should be minus JXS, then power will be maximum power. Now, I have fixed XS and I will vary RL. This is the second stage I am doing. Power will be maximum if RL equal to RS, and this need not be redone, because I have already done it in a circuit. Supply voltage is V, RS, RL, resistive circuit. What is this? So, the final conclusion is that in a circuit, I draw it, this is the AC supply V 0 degree, whatever it is source impedance RS plus jxs. These are the two terminals where I am connecting load, and now I will say I will vary both load and source impedance simultaneously. You imagine you are varying. Then for P max, this is ZL. For P max, ZL must be equal to RL minus JXS, RS minus JXS. Or people say that load impedance should be complex conjugate in general. Although source impedance cannot be capacitive, but for academic interest you can also see if your source has got capacitive input impedance, then the load should be inductive, then R plus J, complex conjugate of that, maximum power transfer will take place. Got the point. And the last case, so this point you see how nicely this problem has been tackled. In general, I wrote this expression. My goal is to find out both RL and XL. I will arbitrarily vary, want to know what should be the value of RSRL. Then I say that look here, instead of trying to vary both of them together, imagine that okay, RL you have fixed some value and only XL you are varying. Then we came to the conclusion, no matter what value of RL you have chosen, maximum power will be only when XL equal to minus XS, because current is to be maximized. Then we allowed RL to vary and XL is set to minus JXS. Finally, the thing is, suppose you have a situation like this, AC circuit, this is a standard topic, this is suppose source impedance JXS, and here is the load impedances ZL I have connected. Z is the load impedance. Suppose I say load impedance is such that it is purely resistive, that is only RL, only RL is connected and I will vary this. Purely resistive load, purely resistive load. What should be RL for maximum power delivered to RL? Once again you will go by this, current is I, here of course one variable I will just give an indication. What will be the magnitude of the current? This is the RMS value of the voltage, V divided by square root of RS plus RL whole square plus XS square, is not? This is the thing. And what is the expression of power for any value of RL? It is I square into RL, which is equal to V square, put the value of the current, sorry. So, V square by RS plus RL whole square plus XS square into RL, this will be the maximum power. Then once again for, because RL appears both in numerator and denominator, you can differentiate dP dRL set to 0, but I always do this, bring this RL below. If you bring this RL below, this can be written as RS by RL plus 1 whole square plus x square by RL. this is correct. This RL you bring and put it inside, no, it is not, it is square is not there. Well, let us not do this, let us do it is like this B square RL, let us do this step, expand this x square plus RL square plus 2 RS into RL plus x square, of which RS and XS are constant. This is constant internal impedance of the source. Then what you do? You bring this RL below, this RL. So, it will be RS square plus X square. Divide this one I group together and divide by RL, this will be the thing, plus RL square by RL, that is RL, plus 2 RS, this will be the thing. All the terms are okay, hopefully 2 RS. So, power will be maximum if the denominator is minimum, because V square is constant in the numerator. So, P will be maximum if denominator is minimum, and denominator minimum will occur if you vary DDRL. This whole thing is RS square plus X square divided by RL plus RL plus 2 RS, this quantity, differentiate it and set it to 0. What will be the differentiation? This will be RS square plus X square, RL square plus RS square plus X square, and this will be minus 1 by RL square, and plus 1, this will give you 1, and differentiation RS being constant is 0, and this is equal to 0, this will be the thing, or you will get RS square plus X square. If you manipulate this, it will be equal to RL square, or RL, which has to be a positive number. So, is this one, which happens to be the magnitude of the source impedance. Therefore, remember, if it is only resistive, the maximum power for this value of RL has to take place. That is, for maximum power, RL is to be set to this. For example, if I say RS plus JXL is 3 plus J4, I will say connect a resistance of 5 ohm and maximum power will be delivered to it. I hope you have understood this. From next class, I will start the application of graph theory in network analysis. Thank you very much.